Hello everyone. In this part of the lecture, I will talk about carry propagation. Uh, in the previous lecture, in the previous part of the lecture, we designed a binary parallel adder as shown in on the screen. And this parallel adder, it's a 4-bit binary parallel adder. So we are using 4 full adders: full adder 1, full adder 2, full adder 3, full adder 4. The first full adder is adding the 2 bits of the two numbers a1, b1. These are the 2 bits of the two number. a1 is the first bit of the first number, b1 is the first bit of the second number. c1 is the input carry at this first position. This full adder 1 adds the 2 bits and the input carry, which is initially 0, and produces the first sum bit, which is s1. The output of this full adder is the output carry C2, which is given as an input to the next full adder, and the job of the next full adder is to add the 2 bits at the next position, the second bit of first number A and the second bit of the second number B, and it produces the second bit of the sum. It internally generates the output carry, which is given as input to the full adder 3, and the job of this full adder 3 is to add the 2 bits at the third position, and so on and so forth. Okay, so there is a problem with this full adder is when the two numbers are provided simultaneously to the 4 full adders, but these 4 full adder would not function at the same time because they are dependent on each other. For example, this full adder 2 is dependent on the 2 bits provided here and the input carry, which is actually the output carry from the full adder on the right. Even though this full adder gets the 2 bits A2 and B2 at the same time when it gets the 2 bits, the full adder 1 gets the 2 bits, but it cannot function on these 2 bits because the sum would be correct only when this full adder consider the output carry from the right full adder, the full adder on the right side. And similarly, this full adder 3, even if it gets the 2 bits at the same time, but it cannot produce the sum until it gets the input carry C3, which is actually dependent on the full adder 2, and this full adder 2 is actually dependent on the full adder 1. And similarly, full adder 4 gets the 2 bits A4 and B4 on time, but it cannot generate the sum bit 4 unless and until it gets the input carry C4, and this C4 can only be available if full adder 3 gets C3 and the 2 inputs, and this C3 can only be available if full adder 2 gets the 2 bits and the input carry. So this full adder 4 would wait for the C4, and this full adder 3 would wait for C3, and this full adder 2 would wait for C2. So this wait, when the carry propagates from full adder 1 to 2, then to 3, and then to 4, this would take some time or would create some delay, which is called carry propagation delay, because the carry propagates from full adder A1 till full adder 4, and it takes time, and this is not good. So this is called carry propagation delay, and we have to look a method how can we avoid carry propagation delay. So binary parallel adder is good, but it has some internal delay and we have to remove it. These are the 3 carry bits that we have to investigate, because the 3 full adder 4, full adder 3, full adder 2 are waiting for C4, C3 and C2. So these 3 carries, internal carries, are problematic and we have to investigate them. To investigate these 3 carries, we have to look back to the full adder that we have used in these blocks, full adder blocks. If we look carefully to this full adder circuit, we have 2 inputs, the 2 bits XY, and we have the input carry, and then it creates the sum bit and the carry bit. If we generalize this circuit, then we would call the first bit as AI, BI, CI is the carry, and SI is the sum, and CI plus 1 is the output carry. To specify it or to make it specific for a particular position, then we can use the value of I as 1 or 2 or 3 or 4 for as many as the number of bits in the numbers. We introduce some intermediate variables in this circuit. This output from the first exclusive OR gate is called PI, which is called carry propagation because it plays a role to propagate the carry forward. The output from the first AND gate is called GI because it plays a role to generate carry. So it is not necessary to use PI and GI. You may use other variables. Variables are used to designate these lines in the Boolean equations. Okay, so PI, the Boolean equation of this line, PI is actually AI exclusive R BI, which is written here. PI is equal to AI exclusive R BI. Similarly, GI is equal to AI dot BI. GI is equal to AI and BI. Dot or AND is not represented here, as we already know from the Boolean algebra. So these are the Boolean equation of PI and GI. Similarly, in terms of PI and GI, we can calculate or derive the equation of SI and CI plus 1. So SI is equal to PI exclusive R CI. SI is equal to PI exclusive R CI. CI plus 1 is equal to PI and CI, PI and CI plus, which is R gate, and GI. GI is taken from here. So these are the Boolean equation of SI, CI plus 1, PI and GI. They are written again here. So what we are actually doing, we are actually trying to design a look ahead carry generator. As the name specifies, or the name shows, this generator would try to predict the carry without waiting for the previous full adder. So these are the 4 equations derived from the previous slides. As we are interested in the carries, so let me take this equation of the carry, the output carry, CI plus 1, GI plus PI CI. So if we use I is equal to 1, then we can calculate C2, as we are interested in C2, C3 and C4 because these 3 carries are the internal carries which put a delay into the addition process. So when we put I is equal to 1, we get this equation. I is 1, then we get C2, G1 plus P1 C1, G1 plus P1 C1. So we get C2. This is simple. So we get C2 in terms of G1, P1 and C1. C1 is the initial carry, which is always 0. Similarly, if we put I is equal to 2 in this equation, then when we put I is equal to 2, then we get C3 is equal to G2 P2 C2, G2 plus P2 C2. But we have already calculated C2 here. If we put the value of C2 here, then we would get this equation. P2 is written in its place, and C2 is replaced with G1 plus P1 C1 from here. Now, using distributive law, this can be opened to this one, G2 plus P2 G1 plus P2 P1 C1. Similarly, if we put I is equal to 3, then we get C4 is equal to G3 P3 C3 right here. C4 is equal to G3 plus P3 C3. But as before, we have already derived C3 here. Just put the value of C3 from this equation. C3 is written here. And if we use distributive law to open this part, we can rewrite this C4 like this: G3 in its own place plus P3 G2 plus P3 P2 G1 P3 P2 G1 plus P3 P2 P1 C1 P3 P2 P1 C1. We have derived the three equations for the internal carries C2, C3 and C4. There is one thing important to note about these three equations. We have only C1 in all these equations, but none of the equation is dependent on the other carry except C1. As C1 is not problematic, because C1 we can keep C1 as 0 initially, and none of the other carries are dependent on the other. For example, C3 is not dependent on C2. There is no C2. We do not see C2 here. Similarly, C4 is not dependent on C3 or C2. So we removed the dependencies between these carries. Now we can implement these carries like this. This is the C2 equation for the logic implementation for C2, which is G1 plus P1 and C1. So C2 is equal to G1, which is taken from here, G1 plus, and then P1 C1. P1 C1 is implemented with this logic AND gate. P1 and C1 is taken from here. So this is P1 C1 or with G1, which gets C2. And similarly we can implement C3, which is equal to G2 plus P2 G1 P2 P1 C1. So this is quite simple. P2 G2 are here, and the other three variables are taken from here. So we implement C3, and similarly C4. C4 can be implemented with the same way. So what we get here, C1, G1, P1, these are the inputs. The next two inputs, G2, P2, G3, P3, and we get C2, C3 and C4. So these carries are not dependent on each other. The only carry that these four carries are dependent on is C1, which is immediately available initially. This is the logic implementation of look-ahead carry generator. As a block diagram, this would be the block diagram of a look-ahead carry generator. There is one thing additional, and that is G4 and P4. It is quite simple to continue with the equation of C4 and extend it and add P4 and G4 to produce C5. But we skipped for simplicity, but it is quite simple to continue with that. Now we have designed look ahead carry generator. Now how can we use this look ahead carry generator to produce a full adder, binary full adder, using look ahead carry generator, and that full adder would be without carry propagation delay, because this look ahead carry generator will look ahead or predict the input and internal input carries, and one full adder will not be dependent on the previous full adder, and obviously this circuit will be fast. So let me continue designing a parallel adder using carry generator. If we look the full adder here, the sum bit is calculated from the PI here. So what we do, this is the first full adder that adds the first two bits. So the sum bit is calculated from the P1 exclusive R with C1. S1 is calculated as P1 exclusive R with C1. So where we get P1 from? P1 is taken from here, because this part creates P1 as we see here. What is P1? P1 is A1 exclusive OR gate B1, which is already we created like here using this exclusive OR gate. So this exclusive OR gate create P1 from the two input bits, which is given as input to this look ahead carry generator, as well as it is given as input to this exclusive OR gate. But this connection has not been shown, otherwise it would just overload this diagram. But practically there would be a connection from P1 to this P1, but this connection is not shown for simplicity. So the first two bits are provided here. The outputs are given as input to look ahead carry generator as well as to this exclusive OR gate, and it will create S1. Similarly for S2, the two bits are given as input to this exclusive OR gate, and AND gate creates P2 G2 given as input to look ahead carry generator, as well as this P2 is connected to this P2, and C2 is taken from the output of this look ahead carry generator here. And similarly for the other two bits of the sum, S3 and S4. Now what we actually did, that we introduced the look ahead carry generator inside these logic gates. These are actually the small scale integrated circuits, and this look ahead carry generator is actually the MSI medium scale integrated circuit chip or package, and we implemented the parallel adder using the carry generator here. And the benefit of this carry generator is that the carries are not dependent on each other. When the 4 bits of the two numbers, the 4 bit of number A, A1, A2, A3 and A4, and the 4 bit of the other number B1, B2, B3 and B4 are available, the sum are calculated immediately, and the sum bits are not waiting for the internal carry. There is no internal carry propagation delay because it has been avoided using the look ahead carry generator. This look ahead carry generator predicts the carries C2, C3 and C4 from these inputs and calculates the sum bit without waiting for the internal carries, because the internal carries are not dependent on each other. This circuit is much efficient than the previous circuit without look ahead carry generator. For further reading and questions, you are advised to please read the book Digital Logic and Computer Design by Maurice Manu, and the presentation slides that I have shared with you. Also, keep a note of queries to be asked during online session. While you are watching or listening to this lecture, keep a list of queries that you want to ask during online session. Thank you.